we may think of a block, let's call it lowercase d, which takes the derivative sort of thing, and the output is d by dt of xt. And with these things, we may consider a block diagram representation. However, we're not going to do that. We will do something else. We will have to use integrators, because differentiators are not suitable for continuous time system block representation for the implementation case of circuits. For circuits, integrators will be necessary. So we will put a cross on top of that, and instead of that we will do something like this. X of t goes into a new representation, which is an integral symbol, you may think of, and the output is an accumulated version from minus infinity to t of x tau d tau. All right? This is the block that we will use. On the other hand, our differential equation is not in the form of that. It's in the differential equation form. We have to convert everything to an integral equation format. And the integral equation format will have a notation with a subscript. What I mean is this. For example, for y sub 0 of t will be y of t itself, which is integrated 0 times. But, for example, y1 of t will be the first accumulant, which is, for this case, for example, we will notate it by x sub 1 of t. Of course, this x sub 1 of t is another time function. It changes with time. It's an accumulation function which varies with time. Therefore, it is a function by itself. And the second integral of that thing will be x sub 2 of t, which is the accumulated version of x1 of t, in other words, if you think of x1 of t as a function by itself. So we are continuously integrating like this. And please remember that an accumulation or an integration is nothing but a convolution with u of t as well. So always remember this. This is therefore integral from minus infinity to t y of tau d tau sort of thing. And y2 of t is this time y sub 1 of t convolved with u of t, or again accumulated version of y sub 1 of t. So y sub 1 tau d tau integrated from minus infinity to t. If you substitute inside y1 of tau, it will be a complicated operation, right? Double integrals will have to come into the picture. So I'm avoiding that. I'm just giving you the impression that in general we have y sub k of t, which is nothing but y sub k minus 1 of t convolved with u of t. So these are the integration formulas. But can we convert our differential equation into an integral equation? The answer is obviously yes. You just need to integrate both sides of the equation again and again. Over there, you have to be careful about the ordering, because, for example, when k is equal to 0, with a0 you are multiplying, or a0 is scaling y of t. When you integrate once, it will be y sub 1 of t. But notice that we have derivatives up to order n, so there will be an nth derivative of y. How can we get rid of the nth derivative, which is the highest derivative order? We have to integrate both sides of the equation n times. We have to take the integrals up to order n from both sides. And then this thing a0 y of t will be integrated n times, and it will reach to y sub n of t. which will be scaled by a0. So a0 will not be the scale of y sub 0 of t anymore. It will be the coefficient or the scale of a0 will be multiplying y sub n of t, because that will be n times integrated. So the ordering is a bit shuffled, and we come up with this new integral equation this time. The running index is still from 0 to n because we integrated n times, and we have ak times y sub n minus k of t. Previously it was yk, or the kth derivative. The kth derivative will yield to n minus kth integral. K times differentiated, n times integrated, so a total of n minus k times integrated is equal to k from 0 to n bk x n minus k of t. So the only difference, the only thing that changes is the order, as you see, if you switch from differential equation to an integral equation. Now from here on, this subscript will correspond to, an increased subscript will correspond to a passing through an integrator. And that's how we will solve this using block diagrams. We have to isolate, or the method is as follows. We isolate y sub 0 of t, which is y of t, at the left-hand side of the equation, and push everything else to the right-hand side part. And y0 happens when k is equal to n. Y sub 0, that is y of t. So k is equal to n, and therefore a sub k will be a sub n. So the scalar, the scaling coefficient of yt is an. And I'm going to put it like this in a parenthesis, in a large parenthesis at the right hand side of the equation. Now all the other terms of the summation except for k is equal to capital N is here. It must be here with a negative sign, and these things exist as they are. So let me first write them. bk x sub n minus k of t. This is the input anyway, and the output is with a minus sign k from 0 to capital N minus 1, because that capital N term is here. I'm leaving it outside. a k y n minus k of t. So this is the thing that we need to implement now with an integral equation. And as a reminder, let me remind you that it works like this. We put an integral symbol, and if this is x sub k, for example, after the integration it becomes a sub k plus 1 of t. Okay, that's how things work. The input part, which is here, where is the eraser? I have to erase the board. Okay. Let's try to draw it here because we need a tall thing. The input portion, which is depicted here, is having more and more integrated versions of x. So we start with an x of t coming into our system, and then we also need an integrated version of it, which is x1 of t, and it is multiplied by something and then integrated again, which produces x2 of t now, and x2 of t is also scaled by something, the corresponding b. The first thing, x of t. Where is x of t? Please be careful about this thing. X of t is when k is equal to n, because that is x0 of t. So when k is n, this becomes bn. So x of t is in fact scaled by bn, not by b0. And similarly, x1 of t is scaled by bn minus 1. And x sub 2 is scaled by bn minus 2, etc. And then we need to combine those things, accumulate, and this will be the output, by the way. And it goes down. Let's draw the final down part. This thing, one before the last, is scaled by b1 and then integrated again, and finally scaled by the last one, which is b sub n. When b sub n is appearing here, it means k is equal to 0. It is therefore scaled by b0. And it goes up like this. So this portion depicts this part, the input system. And it produces a temporary signal. Let's call that signal, I don't know, whatever, W of t, which is here at the output. Now with that W, the other one becomes a feedback system, sort of. If you remember from the last lecture, the output is this time integrated and integrated. Previously it was delayed and delayed. Now it will be from the output, it will be integrated and used, and then integrated again and used like this. Okay? It happens like this. This is y of t, with the input w of t, which is the combined output from here. And they are of course scaled, and they are combined here. And scaled and combined, etc. Now let's take a look at the coefficients. The topmost coefficient is the combination of everything. W is coming from here, and all the other terms with negatively scaled minus a case are combined, coming from here. They are combined, and that top summation term over here corresponds to all the things inside this curly parentheses, and therefore it must be scaled by 1 over an. So we have a scale at the top of 1 over an. How about the other ones? For example, y sub 1 of t. What is the scale coefficient of y sub 1? When does it happen? When k is equal to what? Yeah, when k is equal to n minus 1, this becomes y1. Therefore, the multiplying coefficient is minus a n minus 1. So let me write minus a n minus 1. And then it becomes n minus 2, n minus 3, etc. So the coefficients that are scaling the feedback branches are also evaluated as follows: minus a n minus 2, and it goes on like this to the bottom part. How about the bottom that we have? This is the one before the last. It goes up and finally integrated and scaled and combined. This last one, the last iteration, corresponds to when k is equal to capital N, that is y y0. Sorry, when k is equal to 0, that corresponds to y and n times integrated. So this k becomes n in the end for k is equal to 0, which corresponds to a0 at the bottom branch. So let's put a minus a0 as the bottom branch here, minus a0. This one is minus a1. So it's increasing from the bottom to top in terms of the coefficients. And these are the integrals. Now, do you get the picture about how to eliminate utilization of some of the integrators? How can we benefit from the loss of, from the lack of integrators? How can we eliminate some integrals from here? It's the same idea as we did before. We just need to interchange or replace their places, right? As simple as that. Because again, since it's a linear time invariant system, this system that is executing itself here and this system running here can be interchanged. And let's write this one first and then this one. Then you will notice that the integrators will follow a similar path in the center part. And then we will just erase the double integrators and we will make only one integral in the center part. So finally, let me just draw it and then let's wrap up this LTI business. So the input this time first enters to the feedback portion, which is the second part, which has an integrator here and then comes back, and then another integrator and then comes back and accumulated, and the final integrator is here and it comes back like this, and the coefficients were 1 over an was here, and then minus an minus 1 minus an minus 2, etc. up to minus a1 and minus a0. So this is the second part and I draw it as the first part, and its output produces this kind of a system. And this eventual output is the same y of t. And this is the last integrator at the previously left-hand side, now right-hand side version. And there are scales, of course, and the scales are bn minus 1, bn minus 2, etc. up to b1 and b0. And then, of course, we'll just combine these two integrators because they take the same original signal. Let's call it z of t. That z of t is integrated and z1 of t is obtained both here and here. So this is the same thing. And then that thing is integrated against z1 of t. We produce z2 of t. And then etc. Until the end where we obtain zn of t integrated n times. So you need to combine like this and you just erase it. Okay. Let's not do everything. You have a single branch following from top to bottom, and that single branch is split into two branches, to the left and to the right, to the left and to the right, to the left and to the right, and to the left and to the right. Okay. Maybe I should erase and draw what I mean. like this. A single integrator. A single integrator. One single integrator, and finally it splits into two like this. So this is how you eliminate n of these integrators, and instead of 2n you have n integrators in the center. Now I said previously that when the differential equation order or the difference equation orders at the left hand side of the equation and at the right hand side of the equation, when they are different, one is m, the other one is n, what does the figure look like, I said. And I said it's not very easy. You have to just convince yourselves that you find the correct way of drawing the reduced form. Let's call this one the reduced form. It's even more complicated this case, because the original equation will be given to you in terms of a differential equation. K from 0 to m, ak d by dt y of t is equal to k from 0 to m bk d by dt x of t. Now, sorry, this is n, of course. One of them is and the other one is n. When these two are different, the situation is even more complicated, because you have to solve the complication of integration first. First, you have to push it to an integral form. And you have to integrate both sides of the equation according to whichever one, m or n, is larger. Because you don't want any differential portions, you just want integrator usage. Therefore, if m is larger, then you have to integrate both sides of the equation m times. If n is larger, you have to integrate n times. And then, in that case, some of these things, either from the top or from the bottom, will become empty in terms of integration. So which one becomes empty? Make sure that you are able to solve this thing when m is different than n, either less than or greater than. You have to do that because, again, as I say, I promised to ask you an example question in the examination, both in discrete time and in continuous time. But I tend to make these things 3 and 2. But whichever is 3, whichever is 2, I will just choose when I'm writing the question, both in discrete time and in continuous time. So just make sure that you are able to solve this question that I'm asking now. Differential equations of order 2, 3 and 3, 2 for the continuous example. Similarly for the discrete difference equations, 3, 2 or 2, 3. These are the orders. You should be able to do this, and I'm just giving away two of the questions, part A and part B of the same questions, in discrete time and in continuous time. Draw the block diagrams. That will definitely be a question. What will be other questions? Of course, I will ask you to convolve graphically some signals, and you should expect convolution of two signals which may contain impulses or which may contain several blocks. Okay? Particularly, I enjoy asking convolution with an infinite sequence of an impulse. What is an infinite sequence? Think of it like this. Okay, it's not the follow-up. This is called an impulse train, by the way. K from minus infinity to infinity, delta t minus k times capital T. This capital T is the period of the impulses, the separation between two impulses. And there are infinitely many impulses here. It's a periodic signal consisting of impulses. I usually do that, okay? So I'm telling you, to convolve some signals with this signal. Remember that for each individual impulse you need to replicate, you need to draw the shape, the original shape that you're convolving at the position of the impulse. So you need to replicate all those shapes. And you have to combine that replicated shapes. Okay, this is, for example, another question that I usually ask. And I will ask, of course. What other things can you expect from LTI section? You may expect the check of stability and causality of a system that I give you. For example, I can give you a difference equation, and I may ask you whether it is stable or not. Is this difference equation stable? From that difference equation, you first need to generate the impulse response. I say that, assume that it is causal. So you say y of -1 is 0, y of -2 is 0. Everything was 0. Starting from y0, you input an impulse and you recursively generate the output. We did one example of that. And then that is your h of n, the impulse response. From h of n, just take a look at what is the absolute sum of those values from -infinity to infinity, which is from 0 to infinity, of course, for this case. Is it diverging to infinity? If it is diverging to infinity, then it means it's an unstable system. If it doesn't diverge to infinity, but if that summation is finite with a value, then it is a stable system. For example, that may be a question. Okay? The questions will be the check of linearity, the check of time varying or time invariance property, stability and causality and things like that, plus convolutions, plus drawing of the blocks in discrete time and in continuous time that we saw today. That's what you will expect. The other questions that you may expect for a glimpse of such questions, please take a look at your book and solve all the questions, including the advanced questions at the end. Because, you know, the assessment scale, the evaluation scale for any engineering course, for any graduate level or higher education course, is consisting of several layers. Of course, I will ask you a trivial convolution. Of course, I will ask you some trivial draw things, determine whether it is stable or not, etc. But there will be some levels which will require more thinking, like the advanced questions at the end of the book. So for such questions, please take a look at those things. For an average student is expected to get 60 or something. Not an average student. For a student with the minimum skills, will get 60 from the examination. That is the sufficient skill level. You are able to do calculations. Between 60 and 40 more, which is 100, it means it requires more engineering skills of problem solving. So you have to make sure that you get 60 at least, and then the more the better. It was not like this in the previous years, but the questions will be different, and it's not going to be the same way that we did. In the previous years, I usually asked questions, which is already involved. You have to find the trick. You have to be engineers. And then, once you find the trick, you have to apply your knowledge. So both of them were necessary in all questions. Puzzle solving, engineering skills, and knowledge. It was necessary for all questions, but now, this year, it won't be like that. There will be trivial problem-solving knowledge questions, and you have to answer them correctly. I don't know, 50 or 60, you have to get at a minimum. And below that, you will fail. Because that's the necessary minimum knowledge. Right? It won't be like the previous years. And of course, you will have the tables. I may even let you to prepare a crib sheet, one piece of paper for yourselves, and bring them, bring examination. You will be allowed such things. Because you may not remember some of the things, the formulas, the tabular things. You don't need to memorize those things. But I'm sure that if you solve several questions, automatically you start memorizing them and you just know them. Okay? You remember them. Now, we are finished with the LTI. In the next remaining 5 minutes, I'll try to motivate, make an introduction to the next chapter of Fourier series representation. And we will need 3 more hours before the examination, because there will be easy parts of questions from the Fourier series in the first exam as well, first midterm. So what are Fourier series, and how does it develop? It was developed by this guy. It's the name of a person. Okay, Jean-Baptiste Fourier is a person who lived during the we can call the Renaissance era of the in France, in Paris, where many scientists were just living all together. That's a very good thing, you know. If several scientists or several engineers, several well-thinking people are coming together, then they become productive. If they work alone and if they are far away from each other, then they're not so productive usually. So the atmosphere of Paris in that era was a good one. I recommend that you take a look at my the piece of sheet on top of my door. Okay, there's a paper, a wide one, which shows my genealogical roots. But that genealogy is not in terms of parents or grandparents, etc. It's the advisor and the advisor's advisor, and who is the advisor of that? It goes on like this. It's like a family tree. Okay. And over there, you will notice some parts will go down to Fourier. It will go deeper than that. Then we will mention about his student as well, and his student's student, his professor, and his professor's professor as well. Please take a look at that. It's an enjoyable thing to see how things are working all together and how they boil down to some paths. This guy Fourier is the first one who discovered that a continuous time, even a continuous time signal, consists of, if it is a periodic signal, by the way, we are talking about periodic signals like this. Okay, it's periodically repeating itself with a period of capital T. Such periodic signals can be obtained as a linear combination of a very strange signal, which is a sinusoid. Remember that previously we were expressing every signal in terms of a linear combination of impulses. Previously we said x of t is equal to the integral x of tau delta t minus tau d tau from minus infinity to infinity. So delta t minus taus are shifted versions of impulses, and by linearly combining shifted versions of impulses, by integrating them, that's a combination, and scaling with the necessary value, which is the value of x at that corresponding shift of the impulse. That's quite trivial, but as a linear combination of impulses, you can express any kind of a signal. That's what we have learned already. Now this guy is saying that such x of t's are also linear combination of some scales times sinusoids. And what are those sinusoids? What are the frequencies of them? What are the phases? How much are they shifted? We will see. We will come back to that. And what are these scales? By the way, these scales will have a famous name. They will be called the Fourier series coefficients. That's what we will discover. For a given x of t, there is a formula which gives you one by one what the Fourier series coefficients are. We will see that. But this by itself, this thing is quite astonishing because sinusoids are smooth signals. We know them, right? Cosine or sine, with whatever frequency they may be. Whereas these rectangular pulses that I have drawn here, they are not continuous, they are discontinuous. So how can it be the case that a discontinuous signal can be obtained by adding up many continuous sinusoids? It is strange. And it only works as k goes to infinity, by the way. As an infinite summation, it works. But even then, still, they are smooth functions. So the other scientists, the other famous mathematicians, during the era of Fourier, didn't believe that. Because it's counterintuitive. How can you combine several smooth functions and obtain a discontinuous thing? So the first reaction when he submitted a manuscript to the Journal of Mathematics, the other reviewers, which are the professors, just rejected it because they couldn't believe that it's true. But of course it was true, and the proof was also there, and it opened up in a completely new era. In fact, they not only agreed that okay, it's correct, some of the professors just followed this observation to extend it. For example, Laplace was one of them who didn't believe in Fourier. This can't be, he said in the beginning. And then he not only agreed, okay, this is true, he also extended it to the so-called Laplace Transform, which is an extension of nothing but the Fourier transform. It depends on the Fourier transform. You should know what a Laplace transform is from differential equations. Is that correct? If you have seen the differential equations, you have that parameter S, which is the parameter of Laplace, the Laplace transform. So you already know Laplace transform. We will now see from the Fourier series. And this, the frequency of these sinusoids gives us a new axis. It's not the time axis anymore. Here it is t, but it's the frequency axis. And the book prefers to use radians per second frequency, not hertz. So we will call it an omega. So these Fourier series coefficients will be some magnitudes with the corresponding frequency of that sinusoid, which gives you this shape, is called the spectrum. If you have hi-fi systems at home, there's an equalizer, or there are some Chinese audio systems with so-called Wu meters, like this. The high frequency is sometimes increasing. The bass is here, the high frequencies are there, okay? So that thing is a frequency separation. The high frequency is at the edge, at the right edge, and the low frequency is at the left edge, like this. So that's the representation of the signal on the frequency axis. How much energy does it have at this particular frequency? And this thing then yielded to several topics like control systems and then to telecommunications. Because in telecommunications we know that we have to work or transfer our signal, which is usually low frequency like my speech, to higher frequencies. So the concept of frequency by itself comes from Fourier, from the development of this thing. And we will learn how to find this. and we will learn how to find the particular frequencies, what they are, in the next 3 hours, which we will decide. Okay, so we can stop now.